Our group consists of Andrew Powell, Christopher Beck, myself, Jeffrey White, and Jacob Boardman. Our team advisor is Dr. John Helferty. Our project outline for today, this would be the points that I touch on throughout the presentation. Our mission overview. For our mission statement, we wanted to be able to create a fully autonomous lawnmower that would satisfy the constraints of the ION autonomous lawnmower competition when we first started. We wanted to be able to do this through a cutting field of 10 by 12 meters with a near regular shape at the very end. It will, so we have a 10 meter here to 12 with an irregular square at this side right there. We have a static obstacle right here which we will have to maneuver around, along with a white picket fence at the end here. We wanted to also be able to maximize our efficiency and effectiveness throughout this by using our algorithm. We expected to have this finished within a 20-minute time period, while also being able to mow 75% of the lawn. For our schedule, we have fully implemented the border state, meaning that we are fully able to trace the white line and implement all the corners of our field. From there, we are able to generate a path, but also we have fully designed the mechanical aspects of our system so that we have also tested this manually. For the localization, we have also finished and completed the background subtraction image. However, we have yet to fully implement two key components of our project, one being the close detection system or whisker sensors, the other being the angled localization. Due to the angled localization not being completed, we do not foresee us actually finishing our final design by the time constraint for next week. The system overview for this. Initially, we capture an image of the field while the robot is not in play. So from this image, once the lawnmower enters the field, we can subtract the field that we actually just took an image of and have only the red blob of the actual lawnmower. From there, while this is happening, the lawnmower is actually tracing the white border line. After it traces the white border and has all the corners, it can then mow the path that we generated from the MATLAB code. For the autonomy, we wanted to be able to be fully self-governing, that is, to be fully autonomous, and we wanted to be able to mow 75% of the lawn. Initially, as I was saying, we wanted to implement this using the ALT algorithm. So for the ALT algorithm, it is broken into two states, the border state and the mow state. First off, the border state is that it will enter the field and trace the white line using a line sensor. Once it gets to the end of the white line, it will then turn and designate that as a corner. So as it gets all these corners and gets back to its initial point, it will then show which corner or which two adjacent corners have the largest line. That will become then the primary guideline. From there, it will then make parallel lines based off the radius of our cutting mower blade. So as you can see in this picture, it will then generate all these lines. So then after we have those lines, the intersecting points of that and the border will then generate our serpentine path that we want the lawnmower to follow. This is just the logic of our system integration. And if you have any questions on that, I will be more than happy to go afterwards. So our cutting field, this is the prototype cutting field that we generated. It is 122 centimeters by 86 centimeters with an irregular path to show as we would do in the competition. This is the ideal path that it generated from the actual border detection. The green points are all of our corners. As you can see, there are actually more corners than there are of the white line. That is due to irregular turning. So as it as it went along that line, you can see it passed the white line, so it turned back onto it and followed that until it got to the other corner. The blue line designates the mower path that it actually wants to mow. These 50-point distance is based on the MATLAB code that we generated, and it's on the scale of the MATLAB, so we would have to change that accordingly depending on the scale that we have of the picture. This would be the actual lawnmower path that we generated during the test. As you can see here, we have an overshoot of where we needed to be. That is actually not an overshoot, it is the localization reading the red blob outside. So if you think our camera is directly over this playing field, so at angles it will actually show that the red blob is outside the corner, but it is actually following the white line entirely. Up here you can also see that we had slippage whenever we were turning. This is our trial 2. This just shows our primary guideline. So this primary guideline is highly dependent on where we started. So as you will see in trial 3, it will actually change to a horizontal path. So from there, we actually generated another path this is our actual path for the trial 2. And if you look here, it actually is not the 50 units apart. This is due to our compass having a plus-minus 5-degree tolerance. So as it was turning, it went over or undershot the actual turn. So for trial 3, you can see here that the primary guideline changed to the very top line because we started the lawnmower in the top right corner. And this would be the actual path for that. This raw data is nothing but the coordinates that we actually traced while we were doing the actual states. So we mapped this over top of the actual. So those coordinates were mapped on top of the ideal, points that we wanted to have, and we got this correlation. The correlation can range anywhere from being -1, meaning that it didn't touch any of the points that we wanted it to, or to +1, and that means that we got the exact same path that we wanted. The correlation really doesn't mean anything other than as long as it's getting higher, we know that we're progressing in accuracy of actually getting to a real path. I hope this video works. So I would be showing you a video. I don't know if I have it on my flash drive.
It's in the same folder.
Okay.
2 seconds. It's going.
Hey, I'm Chris Beck. I'm with Andrew Powell. We're on Thomas Lawnmower for Technical. Today we'll be demonstrating our complete algorithm.
I feel like 10 minutes.
So as you can see throughout this, it's actually going through the border state at this moment. So as it gets to the white line, it actually passes the white line slightly and actually moves accordingly and turns onto that path. If you see any irregular turns, that is actually where those irregular points actually come from on the picture I showed you before. So after it gets back to its original point, after this turn, it will then generate a mow path that it will follow. So right now it's generating the path. So now it goes back to its primary guideline and we'll start the actual serpentine path that we wanted it to generate. So as you can see, the actual lawnmower would not really have passed that white line. As I was saying before, it only detects that since the red blob is actually elevated, it sees it as an angle and past that white line. So that goes on for another minute or so. So for our localization, which is actually just the placement of the lawnmower at any specific time, we initially take a picture of the playing field, as I mentioned before, and as the lawnmower enters the playing field, it will detect this red blob, and from there start taking 2 pictures per second so that it can actually map the coordinates of the lawnmower while it's moving. The lawnmower, it then subtracts the image from the original image to get a grayscale picture, and it will generate any of the reflection of any other reds in the picture. It will then look at, and if we know that since our robot has to be at least 300 pixels, that we can subtract anything less than 300 pixels, and hopefully if we have any more than one of these that are greater than 300 pixels, we can then show from the starting position which one is actually our lawnmower and which one is not. Our current prototype. We had to implement a second propeller because we didn't have enough instruction space on the first one, and our propellers are not able to have additional flash memory. So due to that, we also implemented a Manchester coding and 2 handshaking for communicating between the main computer and the master microcontroller rather. We then also introduced a second digital compass to increase the performance. This would increase the performance by decreasing the time that it would take in order for it to give feedback and everything like that. The 2 color detectors for the border state have also been implemented so that it could follow the line. So these two colors detectors sit on either side of the line so that if it moves off in any direction, it will just shift back onto so that it's within this designated space. These two are rather 2 circuits of our home circuit and lawnmower tumbler circuit. If you have any questions on the actual circuitry, we can get back to that in the question section. And for our mechanical design, we have, as I said earlier, we have actually implemented our entire Invacare motors, which we use due to the high use in robotics competitions, as well as being very inexpensive, which we have one right here and one there. We then also created a water-resistant shell to enclose these motor controllers and motors and batteries, which is this picture right here. From there, we also built the chassis directly out of T-slot aluminum. We have also, to simulate that we can put a lawnmower on the inside the middle, we have attached weights to the direct middle of the entire system. And although it's not shown here in this picture, we will have an enclosure up here for all of our electrical components. So any of the propellers and things like that. The reason why we used T-slot aluminum was because that we didn't have to weld anything. It's very easy to manufacture, and since we don't have to weld anything, we have certainty that since we are not in industry, that our welds wouldn't actually hold, that they might not actually hold. From there, we also have our references. Any questions?
Anyone? Dennis?
Yes.
I was taken aback by your plus or minus 5 degree electronic compass accuracy.
Okay.
That's kind of crude, don't you think? And it really impacted your performance, didn't it?
Well, the compass itself is not, its inaccuracy is not plus or minus degrees. That's our threshold. Basically, how the algorithm
What's
works.
the accuracy of the compass that you're
Plus
using?
1 minus degrees. But there's
How much?
plus or minus 1 degrees on the
That's more like a Q than industry standard, or not 5.
Yeah, so what we do is we actually take a bunch of readings and average them together over a certain period, and that's how we increase our
Oh,
performance.
no, but the point was made that he said it was plus minus 5 degrees after, or I got the impression it was 5 degrees after.
Yeah, that's incorrect.
Okay.